Hi, Professor. So, as you know, this is the last part of our examination, and it is to explain question 3 of the take-home exam to you. So basically, we all know that this is introducing a position operator, a position x squared operator, and the Hamiltonian operator to the wave function. So I want to start off by apologizing for my very bad handwriting, and I hope you'll be able to understand somewhat. And a lot of respect for you for actually being able to write neatly on the board, and because we can actually read it, unlike this, like Scrabbles. Okay, so I'm going to start with question A, which is x, the regular position operator. So we all know that A plus and minus is equal to 1 over square root of 2h bar m omega times plus or minus I p, which is momentum, plus m omega x. So this is a raising and lowering operator. So when we want to introduce it to the wave function, in this case, we introduce it as the raising, as the lowering, and both of them at the same time. So that gave us 3 conditions. So, as you can see here, when we introduced the raising operator for the wave function, we did a manipulation, and rewrote the expression x to start off with, rewrote it, and we got x is equal to square root of h bar over 2 times m times w, which is omega, times a plus, and then plus a minus. So in the case for the raising operator, we were able, after the manipulations, after introducing it to the wave function, to get the expression square root of m plus 1 times square root of h bar over 2m omega. And then when we introduced the lowering operator to the wave function, we were able to get square root of m times square root of h bar over 2m omega. And for the last condition is we introduced both of them. And using orthogonal sets and pulling out constants, we were able, after mathematical manipulation, we were able to get the value that the position operator is equal to 0. And that's for question part A, and we were able to get 3 conditions. For x squared, on the other hand, we were able to get 4 conditions. We introduced the raising, lowering operator, and both of them into the wave function. After rewriting it in mathematical manipulation, we were able to get the first condition that square root of m squared minus m times h bar over 2m omega was the first condition that we got. The second one, when we had the lowering operator, that one was the raising operator, by the way. When we had the lowering operator, we got the value of square root of m plus 1 times m plus 2 times h bar over 2m omega. And otherwise than that, when we were through integration, we would get the value of, we would get the squared position operator is equal to 0. When we introduced both of them, the last condition, which is the fourth, and through solving it mathematically, we were able to get the value that it was n plus half times h bar over m omega. So for the last condition, for question part C, when we introduced the Hamiltonian operator, well, the first condition that we knew the Hamiltonian operator was this, and that for the Schrodinger equation, when it was introduced, is equal to this. So through mathematical manipulation, we were able to get 2 conditions. The first condition was that the Hamiltonian operator, after introduced to the wave function, we got that h bar times omega is times n plus half in brackets is one of the conditions, and otherwise the Hamiltonian operator would be 0. So basically for this question, it was using the lowering and raising operators, introducing them to the wave functions, using the physical and mathematical properties that we have learned recently in class, and combine them, and to be able to get different conditions based upon the different operators as we have. As in part A, the position operator, part B, the position operator squared, and part C, the Hamiltonian operator. I hope this was helpful. In my paper itself, it's written out better, and thank you.